I'm first time here, so I was thinking maybe you don't know where I come from. So basically, I just wanted to show a slide where our center. And if you are drone, you can see also mountain. If you just fly a little bit our center above, you can see mountain. It's a very nice area near to Munich, and yeah, with Alps on the back, and it's 1 hour to go there. And for those who are maybe in the field of QCR, you can also be interested in a conference we organize next in 2 years. It will be QCR 2027 in June. It will be more about environmental predictions, also a topic which I will speak here. So what I will be speaking today, it's about challenge which was organized last year, and it was during ICANN 24 conference in Lugano. The idea was to see how well we can predict toxicity. Basically, we were interested to see toxicity against one of the assays for endocrine disruptors. And this was, some timeline was, we had submission and so on, so I will go details. So basically, why we were interested in this toxicity? Why it's important? Why? What does it mean, endocrine disruptors? Well, endocrine disruptors are really bad compounds which released by different means. For example, if you drink water, you can get them because there are some compounds, polychlorinated compounds, which are in walls of bottles, which can go to your body, and it will be not good because if they accumulate, they can make some toxicity. And toxicity can be very different type. Can be endocrine disruptions, can be brain toxicity, development toxicity, very, very different toxicity. So these compounds, they mainly affect human by this media. Basically, they go to thyroid disruptors, diabetes, they can cause obesity, early puberty, and also hyperactivity and so on. So there are a lot of bad effects for these compounds, and basically we would like to avoid them, to find these compounds and say, okay, maybe this compound should be not used anymore or limited use because we know that they are very bad ones. Same for environment. If they release environment, they can cause very bad effects, like a change of sex of fish, for example, whatever. So it's not really good compounds. So how can we detect these compounds? Well, the main way how we can detect is to measure these compounds in some assays. So basically, these compounds, they affect very different points, and basically we can make different assays, measure them, and after this we know whether they're toxic or not toxic. It's quite expensive because once you do this, it's require a lot of efforts. Anyway, last year there was new assays which were developed by EPA, Environmental Protection Agency in the US, where they were interested in transferrin. Transferrin is also potential target for endocrine disruptors because if compound bound to this protein, they basically just do not allow the endogenous ligand to go, and that's the problem. And for this exact target, there were not so many data. Before this, they released 1,500 compounds, but there were only 200 compounds known in literature, which is basically very small. So what they did so-called fluorescence assay, where some compound, this, I don't see. Some compounds can bind and can compete with assay. So first of all, there is probe which binds to TTR, that's transferrin, and this causes some fluorescence. Now, if endogenous ligand, which is L-tyrosine, bind, it will decrease fluorescence because it will just compete with this fluorescence assay, just take it out from the binding pocket, and the fluorescence decrease. If there are compounds which also interfere, they do same role as L-tyrosine. They will bind to the same binding pocket, and again the fluorescence decrease. So this is experimental assay which was developed by EPA. I say there were not so many compounds which were known. So yes, also measuring is very difficult. How can we do this different way? Can we predict these compounds and maybe we just exclude them? This is possible because we can use computational method. We can, for example, represent molecule for machine learning as descriptors, like 1D descriptors, 2D, 3D descriptors, and some descriptors packages are quite large. Like the package shown here can be thousands of descriptors. And once we have this representation, so all chemicals represented the same vector, we can go to traditional machine learning methods, for example. We can use k-nearest neighbor classification. You can just look, is there is a toxic compound, for example, in surrounding of your compounds where to predict. You can do multiple linear regression, support vector machines, and so on. So these are traditional methods which exist in the field since 60s. Like basically, the first application, not for endocrine disruptors, but like this field called QCR, where in 60s, and field developing, new methods appears, and recently we have emergence of new approaches, which are machine learning directly from chemical structures, which are also part of this presentation here, many of them. And for this, we can use novel methods like transformers, like natural language processing methods. And for this, we just need to represent our molecules in such a way that will be understandable to the correct to the methods. So one of the representation of chemical structures, which are basically for chemists like a graph, can be a smile. Smile is like you start to enumerate all atoms in a molecule from some position, and you come with text representation, smile. And as soon as you have smile, use something which can work with text. And text can be recurrent neural networks, can be convolutional networks, can be transformer, LSTM. So just transform problem to the methods which are used in the other field of machine learning. Another presentation, you can use graph. Graph is also very natural presentation, and you can graph neural networks and so on. One of methods what was basically used in challenge, and was one of the winning methods used in challenge, was transformer CNN. This was developed by us. Basically, when you write smile, you can start from any atom. So basically, it doesn't need to specific atom, and you will get different smiles. It's shown on the just shows some variability. And you can ask a computer to predict always same smile, canonical smile, when there is ruler that you just start from the spectrum atom, and you get the same smile, notwithstanding which structure is used. You just have all the times the same smile. This process is very similar to data augmentation in neural networks. And once we have done this, we can ask machine, we give you initial smile, which is any smile, but correct smile for the structure, give us canonical smile. We can use Latin representation as molecular descriptors for example, convolutional neural networks, or we can use for just like concatenate them as for like neural networks. So I just repeat that basically the same, like you have data augmentation, you have this hamster, and you would like to learn hamster, notwithstanding the way how it's presented, some for smile. And this is one type of method. And another type of method, I said, it's just graph neural networks. And in graph neural networks, you can use message patching networks to train network. And after this, you can read either, for example, information about on the atoms or information about atoms and bonds. It's different implementations. This you can use in NPN method. And after this, you can also learn chemical structures. And after this, you have out from this, and you can correlate with activities. So these methods are really becoming more and more used in the field. So we are, chemistry was a little bit always like taking something good from the machine learning, and now this method specifically fitted to the chemistry are become very powerful, which you will see later. Now coming back to the challenge. Challenge was organized as following. The EP submitted to me article for revision for the article. I say, well, it's a good idea. Let's make a challenge. We had some discussion with them. Project and 17th of May, and on 15th of May we also released leaderboard set. I explained why we did this, because if you see its number of data points not so high. So basically you can learn all data if you just submit all zeros, only one value predicted, you can see what are the values. Use this strategy. So say, okay, 15th of August we released everything, and now you have everything, but blind set will be only on the 1st of September. Okay, so why Tox24 challenge? And it was mentioned very previously. So there was another challenge, Tox21. We didn't organize the challenge, but we were one of the winners. So it's a little bit different. We were, so Tox21 challenge was 10 years ago, and that was challenge organized with 12 assays. One assay, this is what we had, that there it was challenged by NIH, and they had 12 different assays where they wanted to see who is providing the best methods. And this is basically the two winners. The first place was by Günter Klambauer and Seppo Hreite group. Meyer was the first author, Deep Talks, and this article was cited, I think, about, I don't know, 1,200 times since the publication. So for me, it was like change in the chemistry. Deep learning came to chemistry. Before this, I think there was no like very good models, whatever. But this was like a new one, showing really something new coming. We were with my student on the second place, and we used shallow neural networks. So it was like two places, deep and shallow. So you see who's winning. So basically, we have to learn deep learning networks. It was quite interesting. Well, they used multitask learning. We didn't use multitask learning, and maybe because of this we lost, but they won. But at that time, we did not implement carefully for this method in what I will show later. Now, once we organized that last challenge, you can see there is a much big interest in the challenge. So last Tox24, there are only 40 teams. We got 70, 80 teams, and this is even a little bit different of number of teams. Here, each new submission was counted as a team. So there were several submissions from Günter Klambauer, for example, and in our Tox24, we said, okay, only one team, you can't participate to other teams. So basically, we wanted to have different teams, not like sense, because many times you can win by chance. Challenge was organized on the challenge was organized on the OChem database, which I will show a little bit also later. And the reason was that basically we had all this system to log in, to have sessions, to know who is submitting what. And this was not the first challenge we organized, but previously we did some scripts and we lost them and so on. So I said, now we should do something, platform which we support. Okay, now I'm going to the winners. Here is the list of winners, and Amidov won with the highest, lowest error. Lowest error is the better. We better can predict a response. And there were other 11 teams who were also called group winners. Why? Because their predictions were non-significantly different compared to the winner. So basically, by chance, of course, any of them could be winner. So we say, okay, one winner is not correct. How we did this? Of course, we used paired sample t-test, and we found which models were not significantly different, and we named all these models as winners. So there were 11 winners of this challenge, not one. And now also we look which models were submitted. I said we organized challenge on OChem website, which allows to develop models, allows to submit. And interestingly, 3 of 11 models were from our website. So people just use data which are there, models, and they won challenge. That was much less effort than to export data, whatever, like other team did. And what was OChem? Basically, why it was interesting, because in OChem we have a very big number of different descriptors. I was showing you only one time descriptors, like AlbaDesc, which is like 6,000 descriptors. But we have very, very different type of descriptors. We have also very different type of methods, including many methods which are representation learning methods, and some of this method just like I can explain many more. We have also quite nice validation procedure where basically we don't allow molecule to be present in training and test set, so it's quite a robust platform. So why do we have so many representation methods and so on? It's really required, because like we see best method, whatever, like first presentation today, that's what was used at least for some translations for the LLM models, but Nashville equations looks better. So here's an idea, a bit different. Each descriptor method see part of a molecule. Our molecule is a complex object, it's 3D object. And this is in our idea, if we use different presentations, if you do different methods, we are like blind monks which are examining an elephant. So each of them see part of molecule, nobody see whole elephant, but if we join knowledge from all of them, we possibly can have much better model, because we can accumulate knowledge from all of them. And that's basically the idea why we're trying to, on this platform, to collect most of data and so on. So basically, all different methods which something appears, we try to add. And OChem was successfully used in a number of challenges. So we were second in NIH, we won another challenge. And like 2 years ago, we also won Kagel's last solubility prediction challenge with again OChem model. And The challenge was to predict solubility of chemical compounds. And there, basically, again, people wanted to see how to predict solubility for novel compounds which are not seen. It was much big data sets. And the use of different presentation, like molecular features, like graphs, like descriptor generation, were used to make this model. And yes, we use, for example, categorical boosting algorithm, decision trees. We combine with neural networks, convolutional neural networks, CNN, what I was showing, and graph neural networks. And the idea was, again, that they all together do something better, and it was really working on this. And this results of challenge. The target property was kappa matrix to how much different prediction is from zero. From zero, it's by data imbalance. And we could see that if we start to combine different models, we have higher values of kappa. And if we combine all models, we got the highest performance, which was winning. Kappa values low, very low here. But this, like data as this. Data which were measured in assays are not always reliable. And this was the best result for the challenge, which basically was competition. Now let's go back to the top models. So as I said, Amidov won the first model, and this is Amidov with Dmitry Makarov, and this is his model. It does not look very impressive, but this is the best what he could get. And consensus model was 4 models, 2 transformer models, and 2 methods based on just decision trees algorithms. Transformers you saw. CatBoost, it's like a decision tree, developed by Yandex, and it's a very powerful method which we found in many applications. Also here, they tested different methods. This method was working the best, and it makes sense. They use this best method, combine it, and find the best results. But they use something from chemistry. They are chemists, so in data set we had a number of mixtures. Number of mixtures, sometimes you have compound which is not well defined because maybe several groups can be there, and basically like it's a mixture of different isomers. And usually what we do, we just select the biggest compound. We just select the biggest fragment because we think its effect is to this biggest fragment. But it makes sense that not all, it's not always working like this, because maybe smaller fragments can also work. So basically, why to exclude them? But majority method and all other groups, they use that method, use that approach. And Amidov, he used these mixtures descriptors. And mixtures you can do different. You can just take 2 compounds. You can just like combine concatenate vectors. You can take descriptors some minus if it's just 2 mixtures, or you can just use like average weighted descriptors. It's a traditional descriptors. Much better for transformer. They don't need this because transformer can read text. So for them, this is very natural. And this is very quite powerful feature because we use text presentation. Transformer can see there is some separation. It's like something very, very promising for this. So they basically, but okay, it's working. It was working. So I was really surprised when they won and just looked what is there because it was a good idea. Another idea was second place was also interesting. Second place was won by Talita Chirino, and she did so-called data augmentation. So basically, you need to have some knowledge in the field. When we announced this challenge on ICANN, after this I was asking people why you did not participate in the challenge. Say, well, we are not sure because we may not have domain knowledge. And she was using some domain knowledge. In the sense, she was using different automers. Automers, you can see here double bonds, for example, can change. Here double bond, here double bond. So basically, you can have like different representation of the same chemicals, and in solution, basically, different automers can exist, and more importantly, like different algorithms when they're reading this text, they interpret different bonds and so on. So enrichment by adding these automers helped her to get second best place. But I would say the second best place was, so basically she just added automers and made model using those molecules. But basically she, we have here the third place winner. They had both the same results. Simply, we had ordering first was first. So basically she submitted before, but basically they took second and third place. They have exactly the same performance, and basically they could be considered as third place shared winners. Now let's look what was used by different teams. And for this, I'm very grateful to Talita Chirino because she could work with most of teams except 2 teams in addition to this article published themselves. And this is always like this. When you submit the challenge, who won, he would submit the article. Other people, it's difficult because they don't have time to write article and so on. And Talita, she was able to convince somehow to all people to participate. And I know that the last team which joined was reviewer of her article. And after this, I asked, maybe you can join because are you submitting your article or not? Say, oh, maybe late. Maybe you can just join her and we will know about your method. So basically, all articles except 2 were published by her, and she basically did overview of different approaches which were used. What we could see here that we could see that basically all models which were used by winners are consensus. So except for model by Wang, who did transfer learning based on gut architecture, they pre-trained a model, and after this they just fine-tuned it on the data. But everybody else was just using this consensus, different approaches, and same idea as we have in this scheme, what I showed before, just to take different presentations, different descriptors, different ideas of different approaches, combine them and have the best performance. Here, for example, one of method which was article which was submitted by Xiaolin Pan. He was just trying now to apply to my group by Marie Curie postdoc. So basically, if somebody would be interested, next year will be called. You can apply. And he was using 3 different representations which were trained, fine-tuned on the data set, and sample prediction, and he also got a good result. Some other methods, for example, very similar to what we have done with transformer. It's like encoder-decoder architecture and intelligent presentation used for model. And malformer, here different idea. Here you mask part of smile. Seems like in the images, and you would like still to get the co-reproduction of the image to complete the image. So all these ideas comes from machine learning. So I think that's what our field. Well, we are more chemists than machine learning experts, but like if there are some new ideas, there are people who are just trying to explore it to see how it works. For example, another Unimol, it's a Chinese company which developed a number of different approaches, and also like working again pre-training of models on large chemical data and so on. And Unimol document was used here. So basically, there are different methods. Of course, this can also try to predict binding. Implicitly used this Unimol document. And I was happy to find that Unimol was developed by one of our students, who is an chemist project, and he presented this method in ICANN conference this year, earlier. So it's basically what we see with these methods. There is quite a variety of things. There are different approaches, and when they join them, we have some good results. We are working in chemical space, and chemical space is a huge one. So can we really predict some kind of compounds, all compounds? For example, if we develop let's say small molecules, after this we go to peptides. Peptides like much bigger. We go to micro. Can we predict reliably? So can we predict unpredictable? No. So basically, there is a concept which is well explored in the field because this is always an issue there. You can, if you have some training set, like here shown in this picture, you can have applicability domain, some compounds which are quite similar to the training set, and in this space you can make reliable predictions. This is something like hallucination of neural networks. Yeah. So here we have good predictions. If you go far, you give some nonsense. They start hallucinate. We don't know what to do. That's basically this is called applicability domain in chemistry. And if compound is a similar one, you can predict. But if compound is a very different one, well, you can't predict reliably. Performance will drop. So like you give something new, I don't know, for say no, I don't know, just like produce nonsense answer, and basically important part here to understand where we are, where we can basically say it's reliable prediction and this is not reliable predictions. Hopefully in chemistry we do more things. So basically, if we see such non-reliable predictions, we can measure compounds. We can measure compounds, and we can extend applicability domain now to these new compounds, like include this compound. And I just show how big chemical space, like there is data set of all compounds up to 17 atoms, only 17 atoms. Drugs can be 60 atoms or even more. And the biggest set, which was used like for solubility in challenge I showed before, 100,000 compounds. So if you would like to predict with this set all compounds from the, this 17 atoms, we will do extrapolation from 1 to 1 million molecules. We can't predict so well all chemicals. We need to know where they are. And now coming back to this again, so accurate prediction, where it comes again from other interpretation. Suppose we have such data, we have a nice correlation, and we are thinking that everything okay, but data coming from nonlinear distribution. So we can't go beyond this. So we need to know where we are. In this case, we say, okay, here we are sure, here we are not sure. And for this, in our field, we have this representation of molecules vectors. We can define distance to model, which can be defined in different ways. Typical use distance from here, Euclidean, Mahalanobis distance, city block, probability density. So basically, you see where your compounds from the training set are, and if it's very different from the test set, in this case, you are sure that maybe this model is not applicable. But in fact, nothing is applicable. If you have such data defined, and not really methods to define this. So for all models, they had defined applicability domains, and basically what is shown here on the on the right columns, if predictions were within applicability domain, they had higher performance. So it makes sense because what is there as compared to those from the test that were without this. And another here, it was like, if you combine applicability domain of different methods, you can have even better performance. So basically, here it's like, if you use consensus of these models, you can have better results, especially for some compounds where everybody agrees. Now, coming back to the challenge, why did we release leaderboard set? Before 15, we had calculated a posteriori of these performances. Talita winning. If we froze submission on this moment, she has the best result, like this error. And once leaderboard set was released, 6 teams got lower root mean square error, so they got better results. These data were really important, and that's why I was saying, I didn't want that people will hack this challenge, will find all data, and because of this they will win challenge. Same. Except data which are used for blind prediction, because this data should stay hidden. And some people didn't want to rebuild model. They just say, okay, we build model using data before, and we don't click. But in fact, if they would do this, they would have better results. And one of the models would be winning challenge, but they never did this. So interesting fact, basically, this leaderboard set, is it good one to see how a model is working for the blind set prediction? This was again by Talita, and she was comparing leaderboard error performance, which was calculated on the website, across the blind test set RMSE, which was not available up to the end of the challenge. And you see, performance is so-so. It's like why it's like this? Because some groups submitted too many predictions. They start to overfit. Blind, this is nothing else. You just input it as part of a training set. So basically, was not working. But she also did some more interesting results. She just looked how would cross-validation results correctly performed would work for the same, and she see much better correlation. So blind test set was used part cross-validation what was used by groups, and that's why it was more correctly predicting the effect. So basically, don't try to fool yourself by just try to be sure how you do this, do correct cross-validation performance estimation, and yeah, don't need to submit best model will not help because you will overfit data. A challenge, and after challenge, basically when we are going to publish like editorial, there was an article which was criticizing our challenge. It was publication by EPA itself. They also participated in the challenge, but did not get, I'm not sure what's participated, but they didn't really, were not amid the winners. And basically they decided to do model as they think would be important for the practical application in APA, which was basically very nice to learn from them, because when we designed, we just said root mean square error, how we can predict signal is good, but in fact they wanted to have which compounds have higher potential to be endocrine disruptors as compared to other compounds. So classification task or a ranking task, not what we have done. And they look for distribution of data, say, yes, you see, data be model, and like we have more active compounds from some 80% of inhibition activity, and we have here, also bimodal distribution, very low activities. And let's do a multi-class classification. Let's just split from 0 to 100 on 11 classes and multi-class classification. Okay, this was the approach, no problem. And also pay attention here, we had less number of active in the test set as compared to training set. This was done because data were split by random, and after this I removed all compounds which were found publicly available as this endocrine disruptors reported literature. This test set was depleted to the number of active compounds. And what they have done, they also look for the quality of data. There was publication just like at the end of the challenge where EPA analyzed data and say, okay, in this data, in fact, some data could degrade. It's chemistry. So you have compounds, you put in the freezer, but it can degrade. And this compound, maybe you have to eliminate them. And after this, number of data points dropped dramatically because quite a number of compounds also removed all mixtures. And say, we would like to protect compounds and multi-class classification, and we would like to do fair experiment. This article was published, we were already like submitting our editorial, but say, okay, let's delay, let's answer this article. And it took us a couple of additional months to understand what they wanted and to make the study. Their main result is here. So basically said, okay, we did our model, multi-class classification, and we have in total 43 active compounds, but so what's here, total number is this number of compounds, and using our model we can recover 33 active compounds which were defined as compound with activity more than 85%. In addition, we have false positives, so we have a number of 28 compounds which were basically false positive, which were not desired, but these were found at bottom. So basically, balance accuracy was 0.8, and sensitivity was 0.77, and this was presented like a very good model for this study. Okay. Usually, whenever I publish something, I try to compare to previous results. So if you claim this, okay, just compare to, and it's okay, you can develop it. Here, and this is their results, basically what they have published, sensitivity, balance accuracy, and after this I just use the same protocol as the best winning model, using their data split, 649, and the test they used, and this model gave by 10% higher sensitivity, balance accuracy. So sorry, the protocol which they were using, it's that provides worse results because this model makes classification task much more easy. So I number of predictions, and its model identified many more active compounds out of 62 or 68 compounds which were predicted as active ones. And so basically, of course, this model was not developed for classification, but the protocol is good. So basically, you can use protocol and you can just put threshold, you can, it works good. After this idea was second one, what will happen if you use all data? Because I use screening of data, they could claim that's important. We used all data, again, test set was not touched, same test set, and model further improved. It's not significant, but it does not show this model was. It's, interesting results. Again, that's for me, it's like if there is some play, I would just to check it, because not like say, okay, this working. And, in addition, they development of model with explainable descriptors, which I will show later. And I was trying also use we have in functional groups, and again, the result was similar, but model was much more explainable. What they did, explainable descriptors, they looked for interactions of the compound with the and they propose some descriptors based on this. But unfortunately, it's not easy to do this with type of descriptors we are using. They were thinking that select some descriptors. This is the best descriptors they found by one of the methods which can rank descriptors. And if you just start to read, first law is log P. It's one of the most important parameters of chemistry. It makes sense, always like this. But second one, well, it's well, you need to have an imagination. What does it mean? And basically, you quite difficult to understand. And this is a model, and model based on more simple stuff, just on functional groups. And before this publication by co-author Aitchison, she showed that some functional groups, like phenol arrays, so compound can have, for example, such group and will be classified as phenols or any group. And basically, you can see that there is high inequality. So basically, some groups are much more represented in high active compound as compared to low active compounds, which are defined by threshold 0.85. So this result, this was not for model, it was published in the article when data. Regression analysis. We have first very explainable model, so it's like again log P, lipophilicity, it's always. But of this is just contribution of different groups. You can just look if this group is present, compound should be active, and so on. So this model is interpretable by chemists. Okay, so basically this model much more interpretable because you just see that okay, some groups are present there and they're likely to provide the contribution to the endpoint. So conclusion was basically if you would like to use, if you like to have interpretable model, use interpretable descriptors. This NLP methods, new methods which are arising in the field, they are much more powerful. You can see which groups contribute there. You can interpret model on the level of smiles because you can look which tokens, in this case atoms, contributing. So I think this is kind of things are going on, and appearance of this new representation learning method, it's not like making things complicated. It's much more. It's making things simpler. Because we can really go with different interpretations. We don't need these uninterpretable descriptors, and we can have also high accuracy. This is what I see like a future development of the field. Now it's like conclusions. So data quality is very important, but data amount too. So if just you eliminate data, you may have lower performance. Machine learning methods are really now very have great power, and these methods really concurrence the field, and it's developing different methods with pre-training, quantum, so and it's really much powerful each day. And the field which was before, it was like has highest accuracy, and when you combine different methods, try to combine diverse models. They should not be correlated. If they are correlated, when your combination will not decrease your bias, will not decrease your variance. But if you have two different methods, like let's say cut boost, decision tree, neural networks, graph neural networks, text presentation, you are contributing very different models which are less correlated, at least by design, and they have mixtures, and merge could be also important. Yeah, these are my conclusions. My participants, like my group is below, and Stephanie, she was, thanks to her, we had challenge. She was kind to wait for not to release data until we have the challenge. And Talita, she was really very kind to make everybody participate in the article, because so it's difficult. I was organizing previous challenge, it like was not possible to publish because not everybody was willing, and like she was able to convince somehow. So thank you for your attention. Yeah, and yeah, if you have questions, we'll be happy to answer.
Thank you for the interesting presentation. I have a question. So, do I understand correctly that Dalita just for every compound in a training set, she calculated tautomers and augmented the data using these tautomers? Am I right?
Yes, but not for all compounds
Yeah, of
tautomer
course.
exist.
Not
So for
every
those which were existing,
Yes.
which are more complicated molecules, she did this. She just used RD kit, which is standard package in chemistry, and so nothing very special, but apparently it was working.
Okay. And
I have many questions. Thank you for the talk. So you had a table where you had RMSE according to the distance from applicability domain, something like that.
It was RMSE due to applicability domain. Yeah, people,
Yeah, so
each group identified applicability domain, and after this they calculated performance as here.
oh yeah,
Just
great.
Mhm.
So my question is, what are the numbers that you want to achieve actually? So if RMSE is 20, is it any useful, or you need like 10, or I don't know?
We would like to have minimum number. Number accuracy is defined by data, measured data. So I think it's about 20. I think maybe or maybe 19. I don't know. So it's basically we see what we have experimental accuracy, and basically we can't go beyond this. So
So
goal is to have minimal error, but we can't go beyond the experimental measurements.
that's what I want to know. So the experimental error is 19-ish?
Well, I think it's less, but I think it's less because they were using these categories and they had used like 11 classes. About, I would say 10 maybe, something like this. Maybe I think there is still some improvement, but yeah. So I think it's a little bit lower, but we probably didn't reach completely the complete accuracy.
I see. So I want to then understand this table. So the best consensus is 19.8, and when you say no AD and with AD,
Yes.
what's the difference?
Not all compounds are covered. Here we cover all compounds from the test set,
Okay.
and here we just cover some compounds which are declared within AD. So we just say, okay,
I see.
these compounds are within AD.
I see. And with consensus, you get 100% coverage within AD.
Yes, and
Oh.
basically once everything was joined, there was no difference. So basically, it's.
I see. So then if I have a class of molecules that are not in AD,
Yeah.
this error goes to what? Like, do you have those numbers, like 25, 30? Is that the case? Or?
For this, you need to do calibration because basically you can define what will be error depending on the distance to model. So basically, compounds which are more similar to the training set, they will have lower performance, lower error. Compounds which are more, so basically depending on the data which you give, you can estimate what will be error for the compounds out of distribution. So that's done. It can't be answered just for one. It's like you calibrate this, and once you do calibration, you can do this.
I see. So some of these papers do that. So if I look up, maybe I
I
can
think
find it.
nobody did this. Basically, did not calibrate because it's like additional kind of feature which wasn't required. So the maximum they did, they just say AD, but calibration first of all require more data because we have data. So data should be done. Training should be done at least by cross. And after this, you can just calibrate and you have this. But usually, what you see, you have like errors start to increase.
Yeah, so I think I'll explain why I'm asking this. So we're trying to develop a method that we want to see how well it can generalize beyond the training set. And for that, we need kind of a benchmark that clearly shows that this is your training set. This is like out of distributions, maybe multiple, as you say, depending on the distance from the training set. And here are the current models, and I want to have some reference to see if we can improve over that. So one thing that I know is this Belka competition last year at New Rips. You don't like that?
For me, it was disaster because when you look for the winners, like was 3,000 places up to win the challenge. Come on.
That's exactly.
No correlation between what they say. I was also thinking to participate, but was not able. Come on, it's just by chance because I think the second place was submitted 2 or 3 times, and he was second place. Come on.
Yeah,
This was
because the test set was very different, right? That was the reason. I mean, the test set and validation set were like completely
you
far
can
from
ask
each other.
organizers. In our case, it was correlation, quite good correlation. And this should be done like this. Otherwise, you just should do what people can predict. You can't tell completely. So I think for me it was, I saw this challenge, but it was like, come on, it's just not correct.
Yeah. So okay. So the question is,
Yeah.
do you in this field, do you have data sets or maybe papers, but okay, data sets that there is predefined sets of training and then like layers of out of distribution, so that we could test these generalization ideas there? Like, could you recommend something like that?
So I would recommend maybe to read papers from a special issue on AI in drug discovery, which was published by Journal of Cheminformatics. And this issue had a number of papers dealing with this problem. So basically, this was a topic of two PhD students in a project which I was coordinating, which was finished this year. And they published a number of articles dealing with this. Personally, I'm still using standard deviation of models as a measure of distance to model. Basically, you can use entropy or whatever, also like this for classification, for example. But the idea is that if models agree, well, probably it's inside of distribution. If the model all disagree, probably we are outside distribution. It's quite well, but according to the new publications, they have better results. Yeah. So you can look for this. I think there are, 2 or 3 papers dealing with this.
I see. Thank you.
Welcome.
Any other questions?
Is there any reasons to look for features and generalization? Because as I see, like you took existing features and did the combination, like linear combination. But maybe you can design some feature which is explainable later by chemists, or like is it a good approach or not?
Well, basically, yes. Chemists would like to know why it's like this. Active, not active compounds. So one way, for example, use explainable descriptors, because like groups, chemistry basically working in terms of groups. You have groups, ionizable groups. So you have, for example, a compound ionized. There is some toxicological, for example, compounds can bind specific site and can toxicity and so on. So chemistry frequently thinking in terms of groups, but each group may be active or not active depending on the environment. So presence of group by itself, it's not like definite answer, because, for example, this group is like covered. It can't go to the protein, can bind. Anyway, explanation in terms of chemical groups is very good, but you can also do explanations of in terms of this NLP methods, of graph methods, where you can, for example, project your predictions. Like you have predicted active compounds. You can project which atoms or beta groups were contributing to this. So yes, you can provide explanation based on the, let's say, featured descriptors, because descriptors created during learning. They will be created during learning, and they can be used to provide explanation to the end user.
So other papers, like they find out the descriptors which can be explainable to groups later, which will like enrich your embeddings and representations.
Well, I think this still, I would say, developing. There are, of course, publications where people try to correlate existing knowledge, chemical knowledge, like, for example, if you predict Ames endpoint, which is mutagenicity, there are known groups, and people try to see whether the network which were built with this data able to find the same group. So there are such works. It's also quite developing. I have my PhD student, she is working on this topic with respect of trying to understand which method can do better explanation. You can use like sharp values, you can use integrated gradients, you can use layer-wise propagation, and after this you have different interpretations. Most important to understand whether they agree or not. Say that there are publications, but still finished, so it's still developing. Yeah.
Okay, thank you. Any other questions?
One more question.
Sure.
So you mentioned that some papers used 3D as input.
Yeah.
But the labels themselves are done on 2D, right? Is this correct to say? Like when you do the experiment, do you know which 3D conformation was that?
No, that's the problem. So basically, there are 3D methods, but first of all, usually these 3D methods, they predict conformational compounds in water. When compound bind to the active site, it changes conformation. So in this respect, maybe docking methods or like quantum chemistry docking, whatever, could be more precise, but we all know that this problem is not easy yet. So basically, prediction binding energies should be defined answering this question, because if you can predict binding energy, it's what we need. But the use of this method is not yet sufficient. Also, problem of conformational flexibility, not only the ligand, which is molecule which bind, but also protein. Protein can also adapt. So predicting information is very important, but usually, quite often, we don't see advantages of 3D information because of the problem of uncertainty. We don't know the conformation is absolute, information change, protein is flexible, so it's too much complexity. So basically, here we had only one showing this 3D, two groups, I think, which were using 3D methods, but the effect maybe was coming from 2D representation, not so much from 2D.
I see. Yeah, thank you.
Again.
There is one more.
Yeah, one thing I was curious about is specifically data set size in this case, right? And how that generally works. Like you mentioned that this was a fairly difficult challenge, and so we're looking at about 1,000 data points. What's overall across these different binding affinities and so on, what do you think is the average data set size? And is this representative in some sense that models that would perform here might perform across many drug targets? Or is this just specific to a specific type of use case?
Well, that set was selected by people from EPA based on their consideration which compounds they are important to investigate. So this was like sampling from different set of compounds. And later on, the article which was shown later, they were trying different strategy. We are using Pareto plot, just trying to understand which additional compounds they need to measure to cover bigger chemical space. Chemicals which like exist.
Yeah, and one of the reasons is that I think what was curious for me is like the kind of ensemble approaches seem very appropriate to having about 1,000 data points, right? So if it was common that there was 100,000 data points, probably the solution looks fairly different because you can learn much more, perhaps more complex features from the training data itself. But I was wondering, I don't know whether these approaches would work, say, if the data training set size was 50 or 100.
Probably, possibly, it's possible to run. It's no problem because you can just take 50 points and see how errors will change. We didn't do, but this can be done. So just to see how, for example, cross-validation error will change, or just prediction out of the training set of compounds will work with the data set size. So we didn't do this. It would be interesting to see whether there is saturation or whether we are still improving. Yeah. So unfortunately, I can't answer this, but it's...
no, it's just interested. I was curious if you knew. Thank you.
Okay, thank you once again for the interesting talk.
Thank you for being here. Thank you for the invitation.